So for this section I'm going to talk about, the artistic hypothesis that I set out with was, what if I were to reorganize a corpus of sounds, in this case recordings, sound recordings, according to their similarity? What would that reorganization look like? What would it sound like? What would that do? And FluCoMa is something that could do this, and I sort of knew that FluCoMa could do this, so I wanted to set out and explore what it would do. Here's the workflow that I went through to do all of this. So the first thing I had to do was choose what my corpus of sound was going to be. What am I actually going to do this analysis and reorganization of, which is not a trivial part of the workflow. I mean, this has a huge impact on the artistic results, right? So not to be overlooked. Carefully curating the corpus is a very important step in the process. At the time, I was asked to write a piece as a remote collaboration with this ensemble, the Switch Ensemble. And so I wrote for them about 2 minutes of music for flute, percussion, piano, and cello. And I sent them the score and had them each individually, because it was a remote collaboration during the pandemic, had them each individually record the audio and video of them performing this score to a click track, so that I could also line it up later if I wanted to, right? So after they did this recording, sent me all of the audio, I had many minutes of audio of music that I had composed. So the corpus, which becomes the data set, is a very personal data set. It is music that I have composed and made with these collaborators, not a sort of big data approach, but really a small data curated corpus approach. And in order to do the decomposition of this many minutes of audio, I could have done something clever, let's say, by using one of the slicers in FluCoMa, doing some sort of analysis and finding onsets and doing the slicing like this. I decided for this project to actually just be a little bit more simple and slice this audio up into 100 millisecond sound slices. So I took all of this many minutes of audio and just said every 100 milliseconds, I'm calling that a new slice. So now I had many thousands of audio slices that were all 100 milliseconds long. The next thing I did was I did some audio analysis on each of these sound slices. You'll see some of the audio analyses along the top here: spectral centroid, spectral spread, there's loudness, pitch confidence. You'll also see on the right there these MFCC coefficients. So I also did MFCC analyses on these audio slices. And after doing all of this analysis, I ended up with actually many hundreds of values for each sound slice. And this is because I not only did the audio analysis, but I also took statistical analyses of these audio analyses to get the mean, standard deviation, minimum, maximum, these sorts of values for these different audio analyses within each sound slice. After having hundreds of values that describe each one of these sound slices in some way, I use 2 different dimensionality reduction algorithms to take these sound slices in these very high dimensional space and reduce them down into a lower dimensional space so that I could start to control them and navigate them a little bit more carefully, or with more intentionality. So here we're looking at it in 2 dimensions because we're on a screen, but actually I reduced it to 11 dimensional space. So now, rather than having hundreds of values that describe each sound slice, I had just 11 values that describe each sound slice. Those 11 values would be able to help me understand the differences between these sound slices and the similarities between these sound slices. So after doing this dimensionality reduction down into 11 dimensional space, I then decided I was going to find a path through this 11 dimensional space that would connect all of the sound slices, visiting each sound slice just one time, and try to make this path as short as possible to connect all the sound slices. And many of you will recognize this as the traveling salesperson problem, a classic problem in computer science. And then once I found a path that I liked, I used this path to simply reorganize these sound slices in time according to this path. And what this will give me, hopefully, is that the sound slices that are near to each other on the path are near to each other on the path, because they are near to each other in that 11-dimensional space, and they're near to each other in that 11-dimensional space because they sound similar, according to their audio analysis. This was the goal of creating this reconstructed sound file. So I ended up with a reconstructed version of this, all of the sound file, using all of the same slices as in the original, but now reorganized according to this path, which hopefully will reflect some measure of perceptual similarity between these sound slices. We're going to listen to this path, this reconstructed sound file, in just a moment. But first, I will orient you to this plot that's on the right. This plot is the result of one of the dimensionality reduction algorithms. It's called UMAP, Uniform Manifold Approximation and Projection. And each one of these dots is one of my sound slices, is a data point. The way that we're looking at it in this two-dimensional space, we cannot perceive like any sort of musical relevance between the X and Y axes. It's not like one of these axes is pitch, one of these axes is loudness. We can't read it like that. But what the dimensionality reduction algorithm does do for us is it will organize these sound slices such that the sound slices that are similar to each other will be near to each other, and the sound slices that are different from each other will end up far apart from each other. And of course, this similarity and difference is based on the audio analyses. So really what I'm saying is the audio analyses are similar to each other. The audio analyses are different from each other. When I had the many hundreds of dimensions, I actually used principal component analysis to reduce it to 11 dimensions. So I just kept the first 11 principal components. That was the first step. And then I used UMAP here to reduce it from the 11 dimensions down to the two-dimensional space we see here. So that's a more thorough explanation. Also, the colors that we see are actually the result of a clustering algorithm, a k-means clustering algorithm that I did in the 11-dimensional space. So basically what I was doing was in the 11-dimensional space, looking for clusters or clumps of data points that were together. And here I'm coloring them all as the same color. It's just another way to sort of peek into that 11-dimensional space and try to see like what types of relationships might be there. So when I hit play, what we're going to do is we're going to hear that reconstructed sound file. And we're also going to see this black line, which is like halfway done in this still image here. We're going to see this black line start to zigzag around, connecting all of these points. And that is actually the path being created in real time as we hear the path unfold in real time. And also what we'll see is on the left, a short video clip of the 100 milliseconds of that performer actually playing that sound slice that we're hearing. So we get a sort of visual representation of the reconstructed path as well. When I did the analysis, I just broke the audio into 100 millisecond chunks. Every 100 milliseconds would be the start of a new slice. When I did the reconstruction of the path, I actually used an overlap of 4. So at any given moment in time, we're actually hearing some part of 4 different sound slices, meaning I'm starting a new slice every 25 milliseconds. And so that's why we see 4 videos, because it's really an overlap of 4. Yeah. Also, the piece was called Quartet. The title came after I finished the piece, but I realized that there are 4 players, but also I often had the 4 players like in these 4 boxes, and so it felt very like quartet-esque. It was about the number 4, etc. So. So that's the result that the algorithm output. When I actually constructed the final version of this section of the piece, I used this output of the algorithm, and I also used a different pathfinding solution. And so I had these two different paths that were reconstructed. And I actually looked through these different paths, these different video files as they end up being. I looked through these different video files and found sections that I really liked. And then actually did some cropping and organizing to do one more pass of this content through my own, aesthetic. And rather than doing a, sort of raw, here's what the algorithm provided output into the final version of the piece. So to be more specific, we're looking at this as a two-dimensional UMAP, which reduces the number of dimensions down to 2. The path that we actually just heard was also created by the UMAP algorithm. Instead of telling UMAP that I wanted it to reduce to 2 dimensions, I told the UMAP I wanted it to reduce to 1 dimension. And so it organized all of the sound slices in 1 dimension, and then I used that organization as the time. The path was actually created in 11-dimensional space, and now we're looking at that path in 2-dimensional space. And so we're sort of having a very distorted view of what that path actually is, whereas in the 11-dimensional space, those jumps might not have actually been quite that large. And the other way to think about this is that this UMAP algorithm is trying to organize what was an 11-dimensional space down to a 1-dimensional space. And that's a very difficult task to do. Like, it's not going to be able to do it perfectly, whatever that would even mean. It's just going to do the best that it can. And in the conclusion of doing the best that it can, it probably has some places where it's like, well, this one is a really big jump, unfortunately, but it's the best that I can do, is sort of another way to think about that.